looking at an example workflow with MapleSim. We're going to start with a robotic model in MapleSim. We're going to generate a controller for that robot in Maple. And then we're going to take that controller and export it to C code for use in a target embedded system. We're also going to look at the output of this process and how it differs from what you'd get from a traditional engineering workflow. So first I'd like to say that there's lots of different ways to incorporate Maple and MapleSim into your workflow. So there's different ways that you can form your model equations in Maple, MapleSim, straight from textbooks even that you can just type into Maple, or importing from tools like Symbolic. And then you do a lot of your analysis and design in Maple itself. And there's a variety of different formats for which you can generate code. And a lot of these are implemented by the MapleSim connector toolboxes. And so you can take a look at what those are on our website to see exactly what's available. The design process we're going to be looking at today starts with a system specification. So in this case, we're going to have a Kuka robot that we want to design for. So it has different lengths and weights of its different pieces. And so that's our system specification. And there's also a performance specification, which is that we want the end effector of the robot to trace out a circular path in 3D space. So the modeling happens in MapleSim. The control design uses that MapleSim model and formulates the equations for the controller in Maple. That controller is then made into a Modelica component, and you can do the simulation in MapleSim to validate that your controller achieves the desired goals. What we're going to be focusing on today is once you have this controller in Maple, you can export the controller to C using our code generation package. And then in a real scenario, you'd be doing some physical tests to validate that your controller performs satisfactorily. So the webinar that we're doing today really builds on a previous webinar that designed a feedback linearization controller for this Kuka robot that you see here. So you can go see that webinar if you want more details on exactly how those equations were worked with to form this controller, but I'll give you a little overview here of what exactly it was that was implemented. So we formed the nonlinear system of equations that represent that Kuka robot. And what we want to do is compute this feedback linearizing controller that linearizes the system with respect to a virtual output function given by sigma. So sigma encoded the distance to the circle that we want the robot to trace and the position along the circle. So it encoded our task really nicely using a small set of functions. And so what we want to do is we want to now build up this linearizing controller in Maple. And this is the outer loop controller. There's an inner loop controller that works as a PD controller. And this is going to get us our desired closed loop dynamics that tells us that our distance to the circle is going to disappear. And we're going to have some desired velocity around the circle. Okay, so let's take a hop into MapleSim and see what we're talking about here. So in MapleSim, the model itself looks very simple, but when we open up these subsystems, you can see that this is the Kuka robot. We have its different links, and there's some revolute joints connecting the links. And so we have some torques coming in, and we're measuring the angles of these joints as our outputs. So previously we designed this feedback linearization controller, and that's what this controller is here. Now, if you want to take this controller and generate code from it, there's a lot of different ways you can do that. And a lot of these are included as attachments that you can attach to your MapleSim model. So these will all use the equations from that subsystem to generate code. And so a lot of the export functionality here is being provided by those MapleSim connector toolboxes. So there's one for BNR automation, there's FMI, there's National Instruments, there's Simulink, block generation. So there's lots of different options. One of the ones up here for code generation will generate C code. And I've already created one of those, so let's open it up and I'll show you what happens by default. So the worksheet's really easy to use, where you just select the subsystem that you want to generate code for. So in this case, our feedback linearization controller. And it identifies what the inputs and outputs are and parameters for the system. In this case, our controller doesn't have any parameters. The gains are hard-coded, but they could be parameters here. And the code generation template will gather all the equations for this component so that it can generate C code for it. One of the really powerful things about this template is that if your equations have differential equations included in them, then it'll also generate the numeric solvers required for your component so that it can be a self-contained unit. And this is what the step 3 is all about. You can then generate C code, and you can take a look at the sample output. So this is output that handles a very generic general case. And it's extremely powerful. And you can see these equations here where actual math operations are being performed is what's really implementing the body of the controller. And some of these other functions are just handling some overhead and some connector functionality. But for the robot that we're looking at today, we designed a controller that's a static function. So there are no dynamics involved. It's just a map from state variables to control inputs. So we can actually generate some C code that's going to be even simpler than what you see here. And so I'm going to show you how you can use the code generation package to do that. So if we go back into MapleSim, what we have is the custom component worksheet. So this is the worksheet from the last webinar. And I've added a few sections to it at the end. So the previous webinar went through taking the equations from the model, forming the controller from those equations, and generating a Modelica component for MapleSim. What we're going to do this time is we're going to pick up from the equations that were created for that Modelica component. In this case, it was a straight line program representing the controller. And we're going to generate C code for it. You can see that this is the entirety of the C code generation for that controller. So taking a set of equations in Maple and turning it into a C function is not a lot of work. So first off, what we do is we actually convert that straight line program into a Maple procedure. And then there's a few little things here that I'm doing to help improve the output. And one of those is that we can explicitly declare the size of the inputs for the function. Calling the code generation C procedure, we then actually translate this Maple procedure into C code. And so this generates a string that we can then write to a file. So right now, we'd already optimized the controller's equations when we were building the Modelica component above. But you could also tell code generation C to do that optimization inline before generating the C code. So it would take the Maple procedure, optimize it to extract common sub-expressions, and put things into a form that's more computationally efficient before converting it to C code. So we can take a look at what the resulting file looks like. So this is the C file here. When we open it up, we can see that the controller has a name that's meaningful to whoever might be using it. And we can see that those arguments for the function have explicit size declarations. And I like this because it makes it easy for analysis tools that might be trying to validate the correctness of these programs to see that there are no illegal array references. All the memory is going to be allocated in a way that's very predictable and very easy to work with for an embedded system. There's a lot of declaration of intermediate variables, and then we get into the actual code that's computing the controller values. So you can see that a lot of these equations are really simple. You have one intermediate variable plus another, one intermediate variable times another. Some of them get more complicated than that. But why it's doing this is that these variables are being reused where they reoccur. So what's happening here is, for example, the cosine function. If you've ever worked with robotics, you'll see that as soon as you start writing down the dynamic equations for the system or the forward kinematics, sines and cosines of those rotary joints appear everywhere, and they're repeated a lot. So if we look at this T133, which is the cosine of x2, we'll just do a find in this document. We find all in current document. You can see that this is actually it was found 102 times. So there's a declaration, there's its first computation. That means it's being reused 100 times after that. You can also see that if you just search for the cosine for that variable is only being calculated once. So you have cosine of x2, x1, and x0, one cosine for each joint. So as many computations as possible are being reused here, which comes down to a really efficient code form. So in the end, at the bottom of the function, you have your controller is going to be assigned the values based on some computation involving all of these intermediate quantities. Okay, so this is what it looks like for a symbolic controller, but what does it look like when you're working in a numeric context? So if you're working in a numeric context, you're starting with the same controller equations, but now you have to compute those derivatives numerically. And so what you can do is you can approximate those derivatives using a forward difference, for example. There's other methods that you can use, like a central difference and higher order differences, but they usually get more computationally expensive, so people stick to something simple like a forward difference. So you have to guess some value of h for which this fraction here gives you a good approximation of the original derivative. So really small values of h in the limit give you a really good approximation of the derivative, but it means that you're subtracting two values of f that are almost the same. So most of the significant digits in f are going to cancel, and you get something that's numerically unstable. It's also something that's a hard engineering question is, what's a good size for h? I've seen some analyses where people can find an optimal value for h, but when you get into a complicated system where your f is going to have elements that are different units, so they could be of very different magnitudes, it gets really tricky to do that. And to compute these Lie derivatives, we need Jacobians and we need Hessians. So if we look at the numerical approximation to the Jacobian, what you see is that you're going to try and approximate this Jacobian matrix using forward differences. So you'd evaluate sigma for different perturbed values of x, form these forward differences, and then this gives you the columns of a matrix. These are columns because sigma was a vector valued function to start with. So to do this, you have to evaluate n perturbed valuations of sigma, where you have n state variables, and then evaluate it once at the actual operating point itself. So you need 7 sigma evaluations. We also need the derivative with respect to the f function, so you need 7 evaluations of f as well. But where things get really complicated is when you need these second order Lie derivatives. So there's LF2 sigma and LGLF sigma. So these involve a Hessian, which is really a third order tensor. You have the derivative of the ith element of sigma with respect to the jth element of x, and with respect to the kth element of x. And so it just gets complicated. What happens when you numerically approximate these is you end up using the forward differences again. You have to calculate now doubly perturbed values of x for evaluating sigma at those points as well. And the number of evaluations you'll need to compute these new terms is n times n plus 1 over 2. So in the case of our example, we had 6 states, and that's going to be 21 evaluations. And it's only 21 because we already know what these perturbed evaluations are, because we can reuse those from the Jacobian computation. So in total, you have to calculate sigma 28 times. So it's something that's, for a relatively simple system, this is already starting to scale rather poorly. Okay, so let's see what the C code for the numeric controller looks like now. So this is one where I've implemented several functions here to provide the functionality I need that Maple is automatically providing to me. So these include some simple linear algebra operations like a matrix add or matrix vector multiply, vector adds. And some of those things were pretty straightforward to implement. The other ones that get more complicated are the Numeric Hessian and Numeric Jacobians. And also you need a linear solver. So you need a numeric solver that can solve a linear set of equations. The sigma, g, and f, these were functions that I actually generated from the MapleSim model. So if you look under here, what I did was I knew that I was going to need sigma, f, and g to implement this numeric controller. So what I did is I took the equations for sigma and I turned them into a procedure. I did the same thing for f and g. So this is a nice way where not only can you export code for that overall controller, but it's easy to just grab subsections of that and just grab a subset of equations and turn those into code as well. So sometimes that can be really useful for debugging purposes, or sometimes in this case for implementing things using a different method. Okay, so we have these functions that were automatically generated and a number of them that had to be manually implemented. And so what we can do is we can now look at what the actual performance of these functions are. So the real question in a target system, in an embedded system, is how fast is my controller? So I did a performance comparison where I ran the controllers many times and then averaged the runtime to determine what an average controller runtime is. So this is done using GCC and Cygwin on Windows. And you can see that I've given it a set of initial conditions. It computes controller values, and the symbolic controller runtime here is reported as less than a microsecond, where the numeric controller runtime is it's almost 11 microseconds. So you have a performance difference of a factor of 14 between the two controllers, which is considerable. One of the reasons for this big difference in performance is that when you're calculating these Jacobians and Hessians, as you differentiate, there's a lot of terms that disappear because you'll have not every component of sigma depends on every x, every state variable in the x. So you'll have some entries in that matrix are 0. When you're forming the controller as a set of equations, those zeros propagate through to cancel out other terms. And so they just disappear and they're automatically simplified away as those 0 terms arise. So you get a significant savings for a system, especially if it has a sparse structure where where all of the output variables do not depend on all of the input variables. But you'll also notice that the two controllers computed different values. So this is arising because there is that forward difference approximation to the derivatives with the numeric controller. So the results that you get for this numeric controller are actually going to depend on that magic value of h that you chose. And for some situations, it's difficult to find a good h, and it's difficult to know how bad your approximation is. So that's why I really don't like using a forward difference derivative. If we take a look at it in Maple, to validate those results, to determine what the controller should have actually calculated, one of the things we can do is we can get the initial conditions for this model, and we can basically get a state vector at which we can evaluate the controller. And that's exactly what I did. I called this controller, symbolic controller, given this state vector, and then it's going to store the result in this control input vector u. So we can see that it's come up with these values, and we'll just take a look at the last one. So it's minus 3357.57. And if we come back into the performance results, 3357.57. So this is the result that was computed by the symbolic controller, and we can see it agrees with the exact value as determined by Maple. And you can see that the error is going to be arising here from that forward difference for the numeric controller. I took a look into the performance of the numeric controller because I found it a little curious that it was such a large difference. And what I found was that it is spending most of the time evaluating the sigma and the f functions. So the performance here is really limited by that explosion in complexity, where you have the Hessians, where you need the second order derivatives, and you just start getting a combinatorial explosion in the number of terms that you have to compute. The more states you have in your system, or the higher order derivatives that you need, the worse this gets. So really, what you can see is that there's some advantages to using the symbolic controller. And one is that it gave us a really simple code structure. So the architecture of the resulting code is incredibly simple. We just have one function, one C function called symbolic controller. Much easier to manage than having the structure that you see with the numeric controller, where you have the numeric controller that I had to implement manually, and then you have F, G, and sigma. I was fortunate enough to be able to automatically generate those, but that's not always the case depending on your situation. And then a whole slew of other functions that were also needed to support the controller. So it just gets more difficult to manage in the life cycle of a project like that. So what we can say in wrapping up here is that when you look at the symbolic versus the numeric controllers, the symbolic controller was less computationally expensive. One of the reasons why this happened was that when you're applying optimizations to the symbolic controller, you can really look at it on a global scale. You're looking at the whole computation sequence as a whole. When you look at the numeric controller, you'd have to optimize each one of those functions individually. And so it's a lot more work. The symbolic derivatives, not only are they more accurate, though, they are also less computationally expensive as well. So there is really a lot of benefits there to using a symbolic approach with the derivatives. The symbolic controller was also more accurate. And again, that's because it was using those symbolic derivatives. And they're not an approximation to the derivatives of the system, but they're exact. And you don't have to worry about what your magic step size is that will give you an accurate derivative. The resulting symbolic controller also had fewer dependencies. So you don't have to have as many linear algebra functions to support your code, and the only function that it was calling external to the aside from the basic arithmetic operations was a pow from math.h, because we had some powers in the model. There's a square root in there, for example. So what happens though is that sometimes the symbolic controller, it might not be able to scale as well for doing it was symbolically solving a linear system of equations as part of that controller. So that there's one small sub-step in the overall controller computation for which the methods used here won't scale to really large systems. But what you can do is you can still break up your computation sequence in one pre-processing step that gives you your A matrix, and then another step that gives you your B vector, and then you can solve for X in your AX equals B system using a numeric linear solver. And those tend to scale better for really large systems. So you can try and mix symbolic and numeric approaches sometimes to really get you something that's highly scalable and that's going to give you the best performance possible. Thank you for your attention, and if you have any questions, please email us. There's lots of material on our website that you can browse and download in terms of the MapleSim model gallery showing you some example models, and we have previous webinars that you can look at. So there's lots of material, and I hope you enjoyed my presentation. Thank you.